Welcome to today's webinar. The topic today is modeling and design of steel structures in Rfem 6. Today I will present the second part of the webinar. Topic is combinations, design and documentation. We start with the state of the last week's webinar, where we modeled the structure and added the loads. My name is Andreas Hörold. I'm responsible for marketing and PR in the company Dlubal Software. I will also present the second part of the webinar. I will be supported by my colleague Niklas Wanke. He's responsible for customer support and also product engineering. He will answer your questions. So I switch off my webcam that you can see the full screen. You can ask questions via the panel. You can click on that question sign here, and then you can enter your question here. And you must press the send button. The other way is to watch the entire webinar and then email questions to info@dlubal.com. To the content today. At first, we will create the load combinations and design situations. They are created automatically, but I give you some hints for that. Then follows the design of the steel components. And we will also consider shear panels and rotational restraint for the purlins. Then follows cross-section optimization. I will consider the stiffness of connections for the design. I create one connection as an example. Then I skip to a model with 4 joints or connections. And we consider the stiffness in the model and take a look at the design results. And the last point for today is the documentation in the printout report. So we start with the final state of the first part of the webinar. We created the model and the loads. Now you can see the load combinations are already created automatically. Now we turn to that dialog in the next step. Before we do that, I switch off for the members, the access systems. Left at the bottom, I switch to the navigator display, then to members, and I switch off the member access systems. Then I turn to the navigator data again, and I would like to switch off the background layer. Now we don't want to see the silo anymore. So deactivate. Okay. Then with a right click to load cases and combinations, I open the dialog. That's the first table of that dialog. The base data, we in the base data of the model, we choose the Eurocode 0 and the German national annex, and we activated the combination wizard. So then, some hints, result combinations. In Rfem 6 and RSTAP 9, the most unfavorable constellations of load combinations are determined in the design situations. You can see the design situations here above. We turn to that later. Wherefore you don't need to create any result combinations for designs in the design add-ons. Generally, load combinations are created for the structure analysis determine nonlinear effects correctly, and result combinations, however, superimpose the results of load cases or combinations, as it may be necessary, for example, for dynamic analysis. Yeah, we don't do the dynamic analysis. That's why we leave that unchecked. So when combination names according to action category then will be load case, and load combinations are not called load case 1 and load case 2, etc., but G, QS, QW, etc. So yeah, that should be all to that dialog. Yeah, construction stages. Yeah, you need that check when the construction stages add-on is activated. Yeah, just if you are interested in using construction stages, then watch our webinars about this add-on. So then we turn to load cases. For the self-weight load case, the structure self-weight is activated by default. That's okay. And we created the other load cases. The general setting is the geometrical linear analysis. The action category controls the superposition of load cases and the partial safety and combination factors according to the selected standard. I can see the different action categories. So then we turn to the actions. Where are different action types simultaneously, alternatively, differently. Simultaneously means all load cases of the action can be combined as desired. If we switch to the wind actions, where are the action type alternatively is activated. Only one of the actions load cases can be effective in the combination, as it is for the wind load case when they come from different directions. So, and differently means load cases can be assigned to groups. Load cases act alternatively within a group, and load cases in different groups can occur simultaneously. Then we turn to the design situations. They are created automatically. And this is the design situation for the ultimate limit state, and those are for the serviceability limit state design. And they must be activated for the add-ons. So, and we can delete these two design situations. We only need the characteristic for the serviceability limit state design. Okay, so then action, we turn at first to the combination wizards. You can see second order analysis. I go to the edit button. The load combinations are preset since nonlinear effects and results according to second order analysis are only correctly determined by load combinations. So then some hints, for example, for the options, user-defined action combinations. No action combination is created, but actions must be combined manually. Then favorable permanent actions. Now, when generating actions, a distinction is made between favorable and unfavorable permanent actions. They are integrated in the superposition by specific partial safety factors. Additional load combinations are created, for example, for design of lifting. But to get not too many combinations, I create two combinations for the design of lifting manually in one of the next steps. So then reduce number of generated combinations. It's a I can call it or describe it as a simplified workflow. All load cases are calculated individually, and based on the calculated values of internal forces and moments, deformations and reactions, you get two groups of load cases for each location. One group contains the load cases with positive values, and the second group includes the load cases with negative values. And the load cases with permanent loads are then combined on the one hand with the load cases from group 1, and the other hand with the load cases from group 2. Then let's turn to the standard options. The options are adapted to the standard. For example, for Eurocode 0, it is possible to neglect certain constellations. But please check the criteria's validity before changing any of the standard options. So we leave all as it is, and we leave the dialog. As I said, the standard is the second order analysis, but the serviceability can be changed to the geometrical linear analysis. And we leave the ultimate limit state design with we use the second order analysis. So then action combinations. As the name suggests, actions are combined now. And from action combination 4, you get 4 load combinations, since there are 4 wind load cases. And action combinations that are not relevant are set inactive by default. So then we turn to the load combinations. And let's go back, from 26, you can see it left at the bottom. From 26 action combinations, you get 177 load combinations. And as I said, it's also possible to add combinations manually. And I would like to add 2 load combinations for the design of lifting. So left at the bottom, I press create new load combination. We use the design situation ultimate limit state, and we assign the self-weight load case and the wind in X direction and with suction. So we enter 0.9 for the self-weight and 1.5 for the wind. So we copy that. And we double click on the load case, and we double click here on the left side, or we can use the arrow to move it on the right side. And then we can change the factor. And now we have created the 2 load combinations for the design of lifting manually. Okay, that's all for this dialog. We start with the design. But before we do that, I turn back to the PowerPoint slides. So there are 3 methods for the stability analysis according to Eurocode. We use method B. We assigned global imperfections in the first part of the webinar. So, and we do a structural analysis according to second order analysis, as I described today. So, and then structural component design on equivalent member according to section 6.3 will be done. But with buckling length, that is equal to the member length. So let's turn back to the program. So the platform beams are held in horizontal direction by the steel plates, and that's why we don't do a stability analysis. But if you would like to do that, I do it for the horizontal beams of the frame, and it's the same workflow would be necessary for the platform beams. But we don't do it for them because of the steel plates that are screwed on the flange of the members. So I select with the pressing the control key. You see the plus sign. All the 6 member sets. So then I do double click. I select the design properties. So, and I switch to the design types. So, and I would like to create new effective lengths. Okay, so the flexible buckling in both directions will be considered, the torsional buckling and the lateral torsional buckling. And the elastic critical moment, mcrit, is determined by the eigenvalue method. So let's select define the nodal supports. We have got one intermediate node. So we select one member set, and you can see the intermediate node, and we hold that node in all directions and about the x-axis. So, and the effective length factors are 1. The nodal supports, when you define the nodal supports, you define the boundary conditions for the eigenvalue analysis, and the effective length factors are for the calculation of the resistance of the single stability shapes. Okay, you can see it in the preview, and that's okay. So I forgot something. I turn back, or I do it another way. In the navigator data, you can see the member sets, and the first 6 member sets are the columns. Oh, sorry, I have to select all and then do a right click, edit. So we go to the design configurations, we leave all as default. We go into it. Now we would like to perform a stability design. But please note, if you don't create effective member lengths or boundary conditions, stability design wouldn't be done. Yeah? So we leave all the factors and standard parameters as they are according to the, those are the values according to the standard. Okay, then serviceability configuration, we also leave the default settings. So then design supports and deflection. For the columns, I would like to define a cantilever beam and we would like to do a serviceability design in that point for the horizontal deformation in both directions. How to do that? I create a design support at member set start for steel. That's all. So, and the program detects automatically cantilever support. So, and in both directions, deformed segment ends. So, okay. Yeah, and you can see it here. So then we continue with the horizontal beams of the frames. I select all of them by pressing the Control key. Then double click. So, and then we go to the design types and I create effective length again. Same dialog, and we leave the effective length factors by 1. Okay. Okay, that's all. Then we continue with that member sets. The longitudinal members of the platform. So double click. I check the design properties, and then the design types. I create effective length. New. Okay, yeah, they don't equal, but yeah, we correct that later. I have got intermediate nodes. So, and I select this one because where are 6 supports? Okay. So, and I hold the intermediate nodes in the weak axis of the beam. And the effective length factors are set to 1. Okay. Okay. So, and yeah, let me go to the navigator display, to the member sets. No, sorry, to the types for steel design and the member effective lengths. And you can see the buckling lengths or effective lengths or factors, effective length factors, and the supports. And if I go to this member set, you can see the program detected that there are only 5 intermediate supports. So over we selected 6 for the other one. But the program assigned it correctly for all. So then only the purlins are missing. I select all the purlins with pressing the Control key, double click. So, and we go to the design types, effective length. So also, with the effective length factors set to 1, and the supports are correct at the end here and the start. So, okay. That should be all for that conditions, but we would like to consider the trapezoidal sheet as roof. How to do that? I select the purlins again. So double click. Sorry, I have to double click that area. So, and then we would like to create beam supports or member supports. So then we create a new member support. So, and rotational. I would like to consider a rotational restraint about the x-axis. So a new dialog is created, and we have to create a new rotational restraint. Continues by the trapezoidal sheet. So continues. We have to select the sheeting material name. For example, what we use S235. Okay. So then a sheeting name. A hash plus T50.1 with a thickness of 0.57 millimeters. Okay. Position of sheeting should be positive. According to the rotational constraint should be determined by Eurocode 3 and this table. So then continuous beam effect. Okay, we did it for the end panel. We start with the internal panel. Okay, so then those values are determined automatically. Let's go to the spring stiffness table. So the position of the sheeting should be positive. Sheet fastened through. The pitch of fastness is in every field. So that's why we use that value. Sheet fastened through the trowel. Okay. So That's all. Yeah, the beam spacing, yeah, we measured. So from this to this, 2.5 meters. Yeah, and we leave that value of on the safety side by 1. Okay. Yeah, I call it continuous internal. Okay. So, okay. Okay. But we did it for all. How to do that? I select all these members, double click. Hinges, sorry, support. And yeah, we create a new member support. So this, sorry, same, rotational restraint, continuous internal. I go to the table, I copy it, so and change that to end panel. So, and this should be okay. Okay, so we have different beam supports now. Let me check it for this one, for example. Support, member support. Internal, exactly. Okay. So let me switch off. I go at the bottom to the navigator display and we uncheck the member effective lengths so that we get a better overview. So now I select all the purlins again, double click on them. So, and it's easier to do that way. Let me turn to the navigator data, then types for members, then member supports. I select all the 2 member supports and edit them. So we leave the rotational restraint, but we would like to add a shear panel in Y direction to both. So eccentricity reference should be at the top. So then shear panel, we create a new shear panel, trapezoidal sheeting. You can also use bracings, trapezoidal sheeting and bracing, and so on. Okay, then I select the same trapezoidal sheeting, Hirsch plus, and T50.1 with that thickness. Okay. So then fastening arrangement in every rib. I measured the shear panel length. This point to that point, 5 meters. define length automatically, the girder length, but I measure the beam spacing. So, and the shear panel coefficients are calculated automatically. Okay. So, and now, the rotational restraint and the shear panel is considered or are considered. So, the stiffness of the member supports is considered in the design, but not in the global calculation. But that would be possible with a structure modification. So now we can start the steel design by pressing that button. That would take several minutes. That's why we switch or return to an already calculated model. As a first overview, you get a warning message. Torsion is neglected for stability design checks, for the purlins, that longitudinal beams. That such internal forces can occur because of the 3D calculation, through the second order analysis, and so on, through, for example, eccentricities, something like that. Let me check how large the internal forces are. We turn left at the bottom to the results, switch to the static analysis. So go to the members, internal forces, and we can see the torsional moments. You can see they are very small. If you want to get such a warning message, you can go to the, for example, to the navigator data, then steel design, to the ultimate configuration. That's the ultimate configuration that we use for the complete design. I double click on it. So, and you can increase, for example, that value. Then you wouldn't get such an error message. We ignore that. So, steel design, design ratios on members. I select the design ratios by section. You can see, for example, for the HEB 240, the maximum design ratio is 0.63 for the deflection in Z direction. So, and then you can also see the other design ratios also in the overview. So let me double click on that line here, and you can see the design checks with the equations from the standard, and you can see where you can find it in the standard. A plastic design is done. We take a look at the section classification that should or was determined automatically. It's class 1. For class 1 and class 2, a plastic design is possible. So then let's take a look at the stability analysis for the column. So you can see the buckling length for the segment, for the lower segment in that case. So, and for this, the n crit is determined by an eigenvalue analysis, and also the n crit. And for that values, the design and the equation from the standards, the design is done. You can also take a look at the diagram in section, stresses, and so on. Yeah, and you can also print that equations directly in the printout report, or you can send it directly to the printer as you wish. So, okay. You can see for the purlins we get very small design check ratios. That's why I would like to show you how you can optimize such a cross section. How to do that? I go to steel design and the input data, then to the table section. So those are the 6 purlins. So, and I use other section for design. I optimize the current row, IPE. So we go to the global add-on settings dialog box. And you can, for example, determine a maximum allowable design ratio, for example, 90% for that section or for the sections. Okay. So, and then we can run the optimization. So that should only take some seconds, because it don't do the global calculation again. It only runs the steel design again. So the program determines calculated an IPE 180. That's quite smaller. But in the next step, you should do press the right button and use the optimize section in the model and run the calculation again. Before we do that, I would like to show you another option. I press the 3 dots here. So, and you can create favorites. How to do that? You can press that button, create new favorites. I call it I-beams equal or smaller than 180 millimeters. Okay. Then we select the IPE 180 with the Shift key. I select all these sections that are equal or smaller than 180 millimeters. Then I press this one, my section, insert selected sections. Then I go to HEA. I select all of them. So plus, and the HEB, all of them plus. So, and then let's go in that table, I-beams that are smaller or that height are smaller than 180 millimeters. You can see the HEAs, HEBs, and IPs. Okay. So, and then and yeah, then you could choose that option, optimize my sections. Now the beams are smaller than 180 millimeters. Now we don't need to do that. We know that the IPE is possible, but I would like to show you the option of the favorites. So, and then you should use the optimize section in the model. Okay, so then the IPE 180 is also in the model, and then we would need to run the calculation again. All load combinations, design situations, the steel design, and so on. Now that should take some time. That's why I switch to the next model. And you can see the purlins are now the IPE 180 with a higher design ratio. Okay, now we turn to the next point of the webinar. I would like to create some one connection as an example, and we would like to consider the rotational stiffness of the connection in the global analysis and also in the design. So I go to the base data and I activate the steel joints add-on. Go to standards 2 according to Eurocode 3 and the German National Annex. Okay. So switch off the results. Then I can click on the node, then right click, create steel joint, or I can go to the navigator data, then types for steel joints and do a right click, new steel joint. But then I have to assign the node. Okay. So let me zoom in. Member 1 is the column, yes. The horizontal beam of the frame, yes. That member, we don't need that member, also that member, also the bracing, this bracing, but the other part of the column is necessary. Then we activate the stiffness analysis configuration, initial stiffness, no interaction. Let me go in the dialog. Initial stiffness is activated, and we leave all the parameters as they are. So then we turn to the members. At least one should be supported, but the type is continuous for both. So, and we want to do a stiffness analysis for the horizontal or for the connection on the horizontal beam, for the normal force and the moment. Okay, then we turn to the components. let me go in the library. So then there are the general categories, the rigid, pinned, truss, and quite new the column base. You can also create column-based joints and bracings. Now I don't define the column base, but that would be possible. So then subcategory beam to continuous column and end plate column stiffness. I apply the template and we should see a preview in some seconds. So you can see the preview. We press OK. And we change the values. I would like to assign 8 bolts. So in the first step, we change the thickness of the plate, 25 millimeters. Top offset should be 90 millimeters. Also the bottom offset, no left offset, and right. Okay. So then the diameter should be M24 and the strength grade 10.9. The spacing horizontally is okay. So, but we change the spacing vertically. But since they are symmetrically, I have to enter only the first 3 values. That was my fault. 4. But the values should be correct anyway. Now you can see they are symmetrical. So we use preloaded bolts and shear panel shouldn't be in the thread. So then I change the welds or the size of the welds. 6, 4, and 6. 6 millimeters for the flanges and 4 millimeters for the web. So then the stiffener, let me check. That's okay. On both sides parallel, we've got 4 stiffeners. I only change the size of the flange welds. Okay. Plausibility check. No errors found. I can also select this node. Okay. Okay. So, and right above, I can display the detailed joint model. And you can see the 2 connections in that area here. So in the same workflow is necessary for the upper connections. I've prepared that. I turn to that model where also these connections are created. So then let me go not to the steel design, to the steel joints design. Design ratios by joints. All the design check ratios are lower than 1. That's okay. So, but we would like to take a look at the stiffness analysis. That's the stiffness for these connections For this one, since we have got assigned only a load in that direction, I assume that's why this value is higher than on this side, but the connections are quite similar. That's why we use these values here. So, and how we consider that stiffnesses, we select at first this horizontal beam. So then we activate hinges, go to the hinges and create a new hinge. With that spring constant. Please note that that is kilonewton meter per rad, and those values are meganewton meter per rad. That's why I add three nulls there. Okay, at the start and at the end. Okay. So, and for this horizontal beam, also hinges. That was the wrong value that I entered. Just a moment, I go back. Hinges. It's easy to change. That's the value for the upper beam. Okay. Okay. So then the lower beam, hinges, go to hinges, same workflow, new hinge, and this time with that spring constant. Okay, at the start and at the end. Okay, so now we need to run the calculation again. That would take some time. That's we turn to the calculated model. Let's take a look at the steel joints results. Those are also okay. Then I turn to the steel design ratios and members. But I've got a better overview for you. Just a moment, I turn to the PowerPoint slide again. So that's the check criterion for the ultimate limit state design. Without on the left side, without consideration of the connection stiffness, and on the right side with the consideration of the connection stiffness. And you can see the values, if you compare them, they are quite similar. For the ultimate limit state design. But when I go to the next slide, the check criterion for the serviceability limit state, you can see there are differences. And for example, for the height of the platform, you get a design ratio of 93%. And with the consideration of the connection stiffness, 108%. Now, what to do? You can increase the stiffness of the connection with ribs or something like that. Or you can consider the connections on the column basis. You can increase the members, or you can say, okay, that's not much higher than 100%. That's up to you. Okay, but what I would like to show you that there are differences if you consider or not consider the stiffness of the connections. So let's turn back to the program. We come to the last point of today's webinar, the documentation in the printout report. Only some example prints I would like to do. For example, the design checks for the steel design. So I print that graphic left above. I print the graphic to the printout report. So that's the preview. We select window filling. That should be all. And then we can press save and show. That's only one example. You can create different views of the steel of the steel construction as you want. I'll show you only examples. Then I press save and show, and then we turn to the printout report manager. You can do different selections. For example, for the steel design, I would like to see the design ratios on members by member set, by member, and so on. And we leave also the steel joint design results in the printout report. Okay. So then the printout report will be created. So that's the printout report with the cover. So it's generating continuously. It takes some seconds. Okay. You can see the result graphic. It's assigned to the steel design. But you can drag and drop it on another place. That's up to you. Now you can see the design ratios on members by member. A lot of results. We have got 264 pages. If you want to edit the printout report content, you can deselect some things. So and if you have got, for example, two screens, you can work in the printout report and in the program at the same time. So let me turn to the cover sheet. So you can do it, for example, a right click and then edit the cover. For example, page setup or other settings. You can enter the name of your company, for example, here. Or you can add another logo. Then you can save it as a template. I load a template. That click Dlubal. Okay. And that is the way we get the company name on the cover sheet. So okay. Okay, I have to change that value. Okay. You can also enter the client created by, it's the same way, edit client, for example, John Doe, etc. So then I would like to show you a multi-print. Go back to Rfem. So without results, the same view. So and then left at the top, print graphics to printout report again. Then I would like to do a multi-print. You can see it on the left side. Multi-print. And above you can see the different dialogues. I don't want to print the current view. No imperfections. No loads. Deselect all. But I would like to show you how you can print results for a selection for the design situation 1, the ultimate limit state design. No global deformations. You could do that for the serviceability limit state design. In the same way. So members, internal forces, for example, N, all internal forces, for example. Then we get 6 pictures. So then we turn back to general. And you can see a preview. Normal forces, the moments, my, mt, and so on. So then I can press save and show. And I open the printout report. You can see the different images here. But as I said, you can move it to another place. Okay, that should be all for this webinar. In the next days, you will get an email with a link to the recording and the finished model. You will get your certificate, your attendee certificate. Thank you for your attention. I hope you liked the webinar. I wish you a nice rest of the day. Bye-bye.